Hello, Assalamu alaikum students. So let's begin with a new chapter on pressure and its measurement. So let's solve some relevant numerical problems. So problem number one, diver descends from the surface of the sea to a depth of 30 meters. What would be the pressure under which the diver would be working above that at the surface? So pressure that is above at the surface pressure, which is atmospheric pressure. So they're basically asking for the gauge pressure, assuming the density of the sea water as 1025 kg per meter cube and it remains constant. So they're asking for the gauge pressure, which is rho gh, and the density is given 1025 and the height is 30 meters. They're basically using the formula with z. I would recommend to simply use the h formula, and remember that the h it is the distance from the water surface to the point. So that is 30 meters, and you get the same answer, 301.7 kilonewton per meter square, which is a pressure unit. So pressure intensity at a point in a fluid is given. It is 3.924 Newton per centimeter square. Find the corresponding height of fluid when the fluid is water, and the second case when it is oil or specific gravity 0.9. So here the pressure intensity is given and they're asking for the corresponding height. So you have to use the same hydrostatic law formula. Pressure is rho gh, and rearrange it for h, the head, which will be pressure over rho g. So for the first case, use the density of water, which is 1000 kg per meter cube, and for the second case, use the density of oil, which is specific gravity 0.9 into density of water 1000, so 900 kg per meter cube. So in case when we have water, we will have 4 meter of water, and for oil having density 900, so this head would be increased by 4.44 meters of oil. An open tank contains water up to a depth of 2 meter, and above it an oil of specific gravity 0.9 for a depth of 1 meter. So from this statement you must be able to draw the figure. An open tank uh, with the water up to a depth of 2 meter, and above it an oil of specific gravity 0.9 for a depth of 1 meter. So find the pressure intensity at the interface of two liquids, that is at point A and at the bottom of the tank. So we know pressure at any depth inside the liquid. This is given by hydrostatic law, which is pressure is equal to rho gh. So for the oil layer, where we have a free surface layer of oil, from that the pressure is simple rho gh. It is easy to compute at the interface. But at the bottom of the tank, the pressure would be because of both the layers, oil and water. And it is best understandable with the help of pressure distribution diagram. As previously discussed, the pressure distribution, it is a triangular shape. The pressure at the water surface is 0, and it increases linearly with the pressure at the bottom equal to rho gh, where rho is the density of the liquid, h is the height of the liquid. Uh, the pressure distribution for this layer, this vertical line. This vertical line represents the 0, 0, and I start with the free surface layer of oil, and the pressure it will increase linearly, and this base pressure it is given by P1. This P1 pressure would be equal to density of the oil into G into H1. H1 is its height. Now this pressure, this will act as a surcharge load. You can say it will act as an overburden for this water layer. So this pressure it will remain constant throughout the water layer, and this pressure this is given as P2. This P2 is equal to P1. you can understand it that the pressure, because of the oil layer, it will act like a surcharge load, additional load on the water layer, which will remain constant throughout the depth of water layer. And the pressure that is exerted by the water to its side, this is P3, and P3, it will be 0 from the water surface, and it increases linearly, equal to the pressure at this base equal to P3, which is given by the density of water into G into the height of this water layer H2. So the pressure at the interface of the two liquid, pressure at A is equal to P1, while at the bottom PB, that is P2 plus P3. So solution is given over here, and solve it, and if you still have any query, we can address it in our online session. The diameters of a small piston and a large piston of a hydraulic jack are 3 cm and 10 cm respectively. A force of 80 Newton is applied on a small piston. Find the load lifted by the large piston when the pistons are at same level, and when the small piston is 40 cm above the large piston. Take the density of liquid in the jack given as 1000 kg per meter cube. Pressure is given by force per unit area. So this force F, which is given 80 newtons, and divided by the area of the small piston, this is equal to the weight W to be lifted by the large piston divided by the area of the large piston. And in this equation, the weight is unknown, so W can be computed by solving the expression. So it came out to be 888.96 Newton. In the second case, they say that the small piston is 40 centimeter above the large piston. So first of all, you have to draw this figure, and you could see there is the height difference. Now we know the pressure at 2 points at same elevation, which might be distance apart in the horizontal dimension, but at same elevation they have same pressure. So we will consider a datum AA for the small piston, and pressure at this datum AA and at this large piston level, it should be equal. So the pressure at the piston, at the small piston level, this is force per unit area, and as we go downward, the pressure increases by rho gh, where rho is the density of this fluid, which is 1000, and h is 40 centimeter. You have to convert it to meters, and that should be equal to W divided by the area of large piston. Now develop the equation, substitute all the values, and simplify and solve for W, and it will come out to be 919.7 newtons. So problem number 5 is very simple. I hope so that you will be able to solve it yourself very easily. Similarly, problem number 6 is very simple. What is the maximum gauge pressure of water that can be measured by means of a piezometer tube that is 2 meter high? And we know pressure using piezometer tube is given by rho gh. So height is 2 meter, density of liquid is 1000 kg per meter cube. The only confusion that could be raised is the maximum gauge pressure, and you know that the piezometer tube is used to measure the gauge pressure. A U-tube manometer similar to that shown is used to measure gauge pressure of a fluid P of density 800 kg per meter cube. If the density of liquid Q is 13.6 × 10⁻³ kg per meter cube, what will be the gauge pressure at A if H1 is 0.5 meter and D is 0.9 meter above BC. And case 2, when H1 is 0.1 meter and D is 0.2 meter below BC. So the first case is same as shown in the figure, that the D point is 0.9 meter above BC. So D point is basically it is higher, or you can say H2 is higher than H1, which is 0.5 meter. So the figure, it correctly represents the scenario. So over here you can simply write the equation with the values for numerical problem. That will be very simple. So we know the pressure at point A is PA, and as we go downward, the pressure would be increased by rho GH1, and then we have reached the datum. So I'll move to point C, and then we are going above, so it will be minus rho man GH2. So this expression could be rearranged for PA, which will be rho man GH2 minus rho GH1. So rho man is 13,600 kg per meter cube. So PA is 13.6 in 10 to the power 3 into 9.81 into 0.9 minus 0.8 into 10 to the power 3 into 9.81 into 0.5. So this came out to be 116.15 into 10 to the power 3 Newton per meter square. So this is very simple. Simply substitute the values. Alright. So moving on to the next case. Next case is little complicated, or you have to understand it. Now here is say that the D point is below BC. So D point lies over here. Here you have D point and it lies 0.2 meter below BC. So this means that you will have to shift your datum. So the new datum must pass through the point D, because below D we know that the liquid, it has same density, so same height, so it will have same pressure. And over here you do not have anything, so this all has to be removed. So D point is open to atmosphere. So writing the pressure equation, it will be PA, and then as we are coming downward, so pressure is increased by rho GH1 plus, as we are coming downward, so plus rho man GH2. Now here the H2 is 0.2 meters and H1 is 0.1 meter. So substitute all the values and you will have this answer in minus 27.45 kilonewton per meter square. So minus sign shows that it is vacuum pressure. Over here I will again advise you not to remember the formula, rather develop the equation for each scenario. A U-tube manometer is arranged as shown to measure the pressure difference between 2 points A and B in a pipeline conveying water of density 1000 kg per meter cube. The density of the manometric fluid is 13.6 in 10 to the power 3 kg per meter cube, and point B is 0.3 meter higher than point A. Calculate the pressure difference when H is 0.7 meter. So in this case, it is told that water is flowing in the pipe, and this manometric fluid is mercury, which is having density 13.6 in 10 to the power 3 kg per meter cube. This H is 0.7, and it is given that point B is 0.3 meter higher than point A. So this B is A plus 0.3. So develop the equation first. We will use the left hand side and right hand side expression. So PA plus rho G A is equal to PB plus rho G B minus H plus rho man GH. So if you have taken my previous lecture, if you have watched the previous video, you must be familiar with what I have said, and you would be able to write the equation. And after that, simply substitute the values and use this relationship that B minus A is 0.3. Again, for the inverted YouTube manometer, I believe now you must be able to solve this. In this case, they have actually asked that calculate the pressure difference PB minus PA. If only the pressure difference is written, you could determine any PA minus PB or PB minus PA. But here they have mentioned it should be PB minus PA. If the top of the manometer is filled with air, and then a second case when it is filled with a oil of relative density, this relative density, actually this is specific gravity 0.8. So the manometric fluid in the first case is air. For air, its density is 1.23 kg per meter cube. So you can basically ignore the density of air. And here they have mentioned it as well. And the second case is when it is filled with an oil of relative density 0.8. The answer came out to be negative. So this